Hello! Today we're going to do a video on phase diagrams, which are part of the unit of intermolecular forces. So let's start off by looking at and defining a phase diagram. On the y-axis, we are looking at pressure, which will usually be given to you in ATM. On the x-axis is temperature, usually in degrees Celsius or in Kelvin. The definition of a phase diagram is a diagram displaying the state of a substance at various pressures and temperatures and the places where there is equilibrium between the three phases. Basically, it will tell you which phase, solid, liquid, or gas, a substance is in at a certain pressure and temperature. In the top left, we have the solid state. In the top right, we have the liquid state. And in the bottom is the gaseous state. The red line shows the boundary, so to speak, between solid and liquid. Technically, it is a curve, but for the sake of simplicity, it is highlighted as a line. Basically, it is the melting point of the substance. If you were to raise the temperature, the pressure at which it becomes liquid will raise too, and vice versa. Melting is when a solid becomes liquid, and freezing is from a liquid to a solid. These terms should be familiar to you. Here, we see the boundary, or interface, between liquid and gas. Basically, this is the boiling point of the substance at specific temperatures and pressures. The transition from a liquid to a gas is vaporization, and from a gas to a liquid is condensation. Again, you should be familiar with these. Here's one that most people aren't familiar with. Solid to gas and vice versa. Along the line, solid and gas is in equilibrium, as before with all the other lines and states. This shows the sublimation point of the substance. Now, here are some terms that might be unfamiliar. When a solid turns to a gas, it is sublimation, and when a gas turns solid, it is deposition. This is the triple point, and it's pretty cool if you ask me. It's where all the states are in equilibrium. Pretty simple. Going back to our previous concept, we can now tie in with the triple point. No liquids can exist beneath the triple point. This is our critical point, the point of critical pressure and critical temperature. Above this, the liquid and vapor can't be distinguished from one another. When that happens, that is called supercritical fluid. Notice the blue dotted lines and remember that they're there just for guidance. There's no point where gas isn't gas anymore or liquid isn't liquid anymore and becomes supercritical fluid. It's just there to give you a general idea of where the supercritical fluid would be. So there you have it, a simple phase diagram. Now it's time to get into details. We're about to look at a phase diagram of water because water is just weird sometimes. Looking at the diagram, there's one thing we can notice straight up. There's a high critical point. This is due to the fact that water has strong van der Waals forces between its molecules. Comparing the water to the simple phase diagram, we can see a slight difference. The slope of the solid and liquid line for water is negative, while for the other one, the slope is positive. This means that for water, as pressure increases, the melting point decreases. Now let's look at a phase diagram for CO2, just for the sake of having another example. This shows why you don't see carbon dioxide as a liquid. You don't get 5.11 atm or higher on Earth. Also, a cool fact about CO2 is that because it has such a low critical point, supercritical CO2 is often used as a solvent to remove nonpolar substances. So there you have it, phase diagrams. I hope you learned something from this video and bye bye.